recording. And so not only are we going to observe physical changes, we're also going to monitor some chemical changes. And so it's important to be able to distinguish between physical and chemical changes. And so therefore, based on our observations, we're going to form hypotheses that are going to explain what we saw. And then we're going to recognize several characteristic properties that are indicative of a chemical change. So therefore, what are some of the things that you will see or hear or smell that will let you know that you are witnessing a chemical change? And so for our miscibility to determine whether or not a liquid is miscible or immiscible in water, what that means is we're trying to determine whether or not that liquid can be dissolved by water. And so the four liquids that we will test to see if they are miscible or immiscible with water are ethanol, hexanol, 1-propanol, and heptane. Miscible means that that liquid can be dissolved by water. And so if the liquid is miscible with water, then what we will be forming when we add that liquid and water together is a homogeneous mixture. The mixture will be constant and uniform throughout. The two liquids will completely dissolve in one another. However, if the liquid is immiscible with water, that means by adding that liquid with water, we have produced a heterogeneous mixture. And for the heterogeneous mixture, the mixture is not going to be uniform throughout. The two liquids will not mix and dissolve completely in each other. In most cases, they don't dissolve at all in each other. And so what you'll see is a boundary line between the two liquids because they will simply not mix with each other. A classic example of this is trying to mix oil and water. Oil is a nonpolar liquid, whereas water is a polar liquid. So the rule for trying to dissolve two liquids in each other is like dissolves like. So water is only going to be able to dissolve other liquids that are also polar. So if you try to dissolve a nonpolar liquid like oil in water, it's not going to happen. And what you'll see is something like this picture here. You have oil in the top layer, water in the bottom layer, and you'll see the boundary line between those two liquids because they just will not mix with each other. And so for the melting point experiment, we're going to use two solids and we're going to determine their melting point range, urea and benzoic acid. And so what the melting point range is the temperature at which the first drop of liquid starts to form, and then the temperature in which all of the liquid has been converted. All of the solid has been converted into a liquid. So that's what we mean by a melting point range. What's the temperature in which the initial melting starts when you see that first drop, and then the final temperature when all of the solid is gone and you only have liquid. And so then we're going to do a chemical changes experiment in which we're going to be reacting two of these chemicals with each other at a time. observe 5 different reactions by combining 2 of these chemicals with each other at a time. And so in making scientific observations and therefore collecting data, we can think about it as happening in a 3-step process. You first observe, and then you record what you are observing using your senses. And then once you've collected the data, you'll analyze the data and make some generalizations, searching for patterns or relationships in the data. And then hypothesizing. Based on what you've seen, what can you conclude? And so as you are making your observations, you can write down your observations, and then you can make a hypothesis based on your observations. And so an example of this, if you have some mercury 2 oxide in a test tube, and this is a solid, and then you heat it over a Bunsen burner flame for about 2 minutes. And then you take a wooden splint, which is just a piece of wood, and it's ignited. And once it starts burning really good, you get a good flame. Then you extinguish it, but the wooden splint will still have lots of heat that is absorbed, so it will still be glowing. And then once you extinguish the fire, but it's still red hot and glowing, you put that glowing splint in your test tube where the mercury oxide is, and then you make your observations. And so the mercury 2 oxide is a solid. It's also an orange powder in color. But then during the heating of that iron, that mercury 2 oxide with that hot wooden splint, it changes from orange and solid to a liquid with a silvery metallic color. And then after several seconds, the glowing splint, wooden splint that you put in the test tube, it reignites by itself. It bursts into flame. So what are some things based on these observations? What are some hypotheses that you can make? Well, you can hypothesize that you just witnessed a chemical change, and then you can justify that based on you got some new products. You started out with an orange substance and you ended up with something that looked totally different. So that lets you know that the chemical identity of the starting material has changed and you have produced a new product. And you can also hypothesize that the new product, the reactant was a solid, your product is a liquid. And so therefore this silvery metallic looking liquid, you can hypothesize that to be mercury. Because if you've ever seen an old-fashioned mercury thermometer, you notice that the mercury reacts to changes in temperature. It will rise and fall inside of that column, which is the thermometer. And so you can hypothesize that the product is pure silver, pure mercury metal. And at room temperatures and at temperatures higher than room temperature, mercury is one of 2 elements on the periodic table that exist as a liquid at room temperature. The other one is bromine. But the majority of metals, of course, are going to be solids at room temperature. And most of your nonmetals on the right-hand side of the periodic table, most are gases at room temperature. But bromine is an exception to that. Bromine is a liquid at room temperature. And mercury is a metal, but at room temperature, it's not a solid. At room temperature, it's actually a liquid. And the reason why it's a solid as mercury oxide, because it's bound, has chemical bonds to oxygen. And so in its oxide form, it's a solid powder. But once you do a chemical reaction and break those bonds between the mercury and the oxygens, and you free the mercury from the oxygens, then it's going to be in the liquid state as a pure mercury metal. And so you can also hypothesize that oxygen is one of the products. And combustion reactions, and the fact that in order to combust or burn something, there must be oxygen present. And so that wooden splint bursting back into flames once inside of the test tube lets you know that that wooden splint combusted. And in order for it to combust, there had to be some free oxygen available in that test tube. And so therefore the reaction produced not only pure mercury metal, but also oxygen was released, because that mercury and oxygen, they work chemically bound together, which gives you that orange powder, mercury oxide. But the chemical reaction that is catalyzed by the heat from that hot glowing splint breaks the bonds between the mercury and the oxygen, and you produce free mercury metal, and you've got some oxygen gas. And so based on all of those observations, we were able to form those three hypotheses. And so that's what you're going to be doing today. Based on your observations, then you're going to hypothesize whether or not you witnessed a physical change or a chemical change. And you're going to be very specific in what you observed and specific in what that means. If it was a chemical change, okay, did you produce a gas like oxygen? During the reaction, was a gas like oxygen produced? Based on what you observed, was heat produced? Was heat absorbed? Did a solid precipitate form? Did a color change happen? Did